So the Wittig reaction is where we take a ketone and an alkyl halide and a bunch of other stuff, which we'll see in just a minute, and we make a carbon-carbon double bond. The important thing to remember is look at your alkene. There's your alkene, and then you just remove a hydrogen and the chlorine and clip the other side of the double bond. So in terms of looking at it from a synthetic standpoint to make a double bond, you're just cutting your oxygen off and you're inserting the carbon from the alkyl halide to make your double bond. So let's take a look at how this reaction is actually done. Okay, so we start off the reaction by making our ylide, and our ylide we'll see in just a second. We take our chloride and we react this with something like, we use this one a lot, triphenylphosphine. We can use other phosphates as well, but this is just a nucleophile, and it kicks off that chlorine, and we form this thing. I'm going to put one of my hydrogens down. We actually make a salt, okay? We have a positive charge on the phosphorus. Chloride has come off as chloride. It's a salt. Then the next step of the reaction, we use a strong base, and we might use something like sodium amide. And this is the thing we call an ylide. I'm going to put a pair of electrons there. This now has a negative charge. It's bonded to our phosphorus, which has a positive charge. And now we've also formed, because we used this pulled off a proton, so we have ammonia, we have sodium, and we have chloride. All of those things are now just sitting there watching the rest of this reaction happen. At this point, we would introduce our ketone, and when we introduce our ketone, I'm going to draw it down here. And we have a negatively charged carbon. That's a good nucleophile, so it's just going to attack the carbonyl compound. We're going to go up there. We're going to make this new compound. Put my H up here, my phosphorus I'm going to put here. Look at everything I've done there. This lone pair of electrons is the nucleophilic pair of electrons, and it attacks the electrophilic carbon of the carbonyl group to form a carbon-carbon bond. And then we threw our electrons that were in the pi bond, because carbon can only have 4 bonds, we have to throw one of those up onto the oxygen. We have this negatively charged oxygen. Now from here, this is what's postulated to occur, is that when this initially forms, these things are too far away to form a bond. They rotate and they just form a bond. We don't want to be too upset about our fact that we have a whole bunch of bonds to the phosphorus, because it is, after all, phosphorus. It's down below the second row. We can expand its valency beyond an octet, so we're okay with that. We've now formed this thing. Looks like a butane type of thing, but we have a phosphorus and an oxygen in it. And now we just have to think about how we're going to break this apart, and we can push our arrows. We can push them either way. I'm going to push them this way. We form a phosphorus oxygen double bond. We break the carbon oxygen bond. We form a carbon carbon double bond, and we also broke the carbon carbon. So we end up with, I'm going to put it down here, our R C H double bond C. Sorry for those of you. Okay, so this part, oh, that's exactly behind here. So can you see it? Okay, let me try over here. So this is what I drew over there. We have R, C, H, double bond, C, here's the pH, and here's the Ne. Let's erase the rest of this now, just so it's not in the way. We'll draw a big long arrow. We drew that thing, and the other thing we made was our phosphorus. So in a way, the phosphorus just removed the oxygen from the carbonyl compound, and we placed in its stead the thing that came from the alkyl bromide. So here's our carbon-carbon double bond, okay? So that's the mechanism for the Wittig reaction.